All right, good morning, ladies and gentlemen. It is March 15th. Welcome back to ICP. Today, we're going to be talking about fusion versus fission. So two very important reactions. They're going to build on our discussion last week of electricity. These are two ways that we can generate enormous amounts of energy, and one we actually use to make electricity today and one which we hope to use in the future. So without further ado, let's go ahead and get started and then share my screen to show you where we are at specifically. So if you go to the Google Classroom, we are working on day 21, so that should be under the videos. Day 21, fusion versus fission. We've got notes, just mostly notes, and then the X ticket. There's actually not practice for this one. This is the last new material of ICP. So just a reminder, tomorrow we are going to be zooming in together to review for the final exam, and then that will open up on Wednesday for you to take the final exam. It needs to be done Wednesday so I can have it graded and put in the grade book before the end of the term, because this is the last week of the term, so there's really only a couple days left of class. So if you have any missing assignments or any tests that you need to make up or make corrections on or retakes, you need to get that done as soon as possible. So if you need to do that, please reach out to me so we can set something up. But okay, let's go ahead and get into fusion versus fission. So go ahead and open up the Google guided notes, the Google Doc, and we'll get started. Okay, let's think about the atom. Okay, in the nucleus of an atom, there are two things. There are protons, which have a positive charge, and neutrons, which have no charge. So here's the question. If there's so many positive forces, right, positive protons in such a close proximity, how is that held together? Because what do we know about like charges? When you get two like charges close together, they repel each other, right? There's a push away, that repulsion force. So then how can we add so many protons in the nucleus of an atom without them breaking apart? Well, there's obviously some other forces holding the nucleus of the atom together. And those forces are called strong nuclear forces. So the strong nuclear forces are actually a slightly stronger force than the repulsion force of the like charges. However, this doesn't always hold true as atoms get larger and larger and larger. At a certain point, atoms get so big and there's so many positive protons packed into that small, dense nucleus that they actually become unstable. And that's what we're going to be talking about today. When they become unstable, they're going to break apart and they're going to give off some energy. Okay, and that's what we call radioactivity. So late 1800s, we had a gentleman by the name of Henry Becquerel, and he was actually working with uranium salt, and he had accidentally left some on top of a photographic plate in one of his drawers. Now, when he developed that photographic plate, he saw the outline of the uranium salt on it. And the only way that that could work is if that uranium was giving off some kind of energy that darkened the film. So that's the key. He realized at that point that the only way that that photographic plate could have been exposed to something is it had to be exposed to some kind of energy. Normally we just use light, right? The light, the photograph, the camera opens, exposes the photographic plate to light. That image is burned onto the plate itself, and then it can be later developed into a photograph. So he kind of hypothesized that the uranium salt had to be giving off some kind of energy so that the plate could actually become exposed and you could see the outline of the uranium salt. All right. 2 years later, some other people also kind of took that idea and ran with it. Marie and Pierre Curie. They looked at polonium and radium and found that those were also both radioactive. So now we have uranium, polonium, and radium, and all three of these are radioactive. So as we continue to identify elements that are radioactive, we've started to see a pattern. And that pattern is that any element over atomic number 83 is radioactive. So atomic number 83, that element is, 83 is bismuth, okay? And bismuth is the largest atom that is not radioactive. After 80, when you get to 84, that's polonium. That's one of the first radioactive elements. So what does that mean? Well, radioactive materials have an unstable nucleus because it either has too many or too few neutrons. We believe that neutrons, or the subparts of neutrons, play a part in holding the atom together, the nucleus of the atom together. But we don't fully have a clear understanding of how all this works, but here's the key. If it has too many or too few of those neutrons, in the nucleus, the nuclei itself becomes unstable and can break apart. So when it breaks apart, we call it decaying. It breaks apart, it gives off particles and energy. Remember, nothing can be created or destroyed, so it has to come from somewhere, it has to go somewhere. So if we're breaking apart and we're losing some mass or we're getting smaller, it's going to release some particles as it decays. That's key. So those particles might be alpha particles, beta particles, or gamma radiation. Okay, so these are all three things given off in addition to something else we're going to talk about that's very important when an element decays. All right, so let's talk about the first process, which is fission, okay? Fission. Fission is the process used to release nuclear energy by splitting a uranium-235 nuclei. Okay, now uranium-235, that is an isotope. And we haven't talked much about them since when we talked all the way back on the periodic table. So just remember, an isotope is an element that has the same number of protons, right? But it has a different number of neutrons. Oops, excuse me, different number of neutrons. So the key here is that it is very unstable. So what we can see here is this is the uranium nucleus. Uranium is radioactive. Okay. Hang on. In the middle of a recording, let me pause it. All right, guys, apologize for the interruption. Let's go ahead and get back to the notes. I believe we were here. Okay. All right. So again, fission, we start with a large nucleus, right? Large atom. In this case, it's uranium-235, one of those isotopes. We give it a little push. That's key. You need to give it a little push to start it to break down. But then once you give it that little push, it's going to split apart. It's going to release a bunch of stuff, and it's going to. Okay, I just want to make sure we got all this stuff. I am going backwards. Hold on. What happens when I get interrupted in the middle of a lesson? Okay, so again, fission, starting with a large nucleus, unstable. It's going to break down to smaller things and release neutrons and then a whole bunch of energy. Okay, so the key here is only large nuclei like uranium or plutonium can split apart during nuclear fission. So here we have uranium, and we are going to add a little extra neutron to it that causes the already unstable nucleus to become completely unstable and break apart. So again, we add a little neutron, big nucleus, breaks apart. Now, look, it turns into barium and krypton, atomic number 56 and atomic number 36. Now, if you add 56 and 36 together, guess what you get? You get 92. No protons are being created or destroyed. They're just being split into two smaller things. So we get two smaller elements. Okay, it immediately splits. We get barium and krypton, several neutrons, and then a huge amount of energy. Okay, now what did we have to add in? We had to add in a neutron. And what else came out? We had some other neutrons coming out of this reaction. So you can see how if we have a bunch of uranium together and we give it a little push, these free neutrons can then go and hit other uranium atoms, starting this process all over again. So this is key, the fact that this can be a continual process, a chain reaction, once it's been started. So like I said, the free neutrons produced by fission can hit other nuclei, which causes them to split, release even more neutrons, free neutrons, and it happens again and again and again. When that occurs, we call it a chain reaction. Now, the problem is if this chain reaction is uncontrolled, which means it just gets to happen as fast as it can naturally happen, well, then we can get a nuclear explosion. Then the energy builds up too quickly, we can't control it, and we get that big boom. However, we can slow it down by using things that will absorb neutrons. So materials like lead are really good at taking in lots and lots and lots of free neutrons. So a lot of times we'll have lead in the chamber where this reaction is taking place to help slow down that uranium reaction. So an uncontrolled chain reaction releases a huge amount of energy in a very short time, but just requires a critical mass of starting material. So obviously we have used fission and a fission bomb, the atomic bomb, and nuclear weaponry. What you need to understand about those is actually two bombs in one, right? There's a little bomb to start the reaction, and then the big bomb, once that reaction has started, is the whole fission chain reaction. So requires a critical mass of starting material to produce more reactions. Now, obviously, we don't just use this in weaponry. We were talking about this when we talk about electricity. So obviously, we can use this reaction because it produces a lot of energy to generate electricity. So let's take a look at how that happens. This is called nuclear power. So nuclear power plants use fission to produce electricity. Nuclear power is used in many countries. France is actually the current leader. It has the most percentage of its energy budget being filled by nuclear energy. Ours is mostly by coal and natural gas. So we burn coal and natural gas to produce steam. That steam, right, to heat water and produce steam. That steam then powers a turbine, and that motion generates electricity. However, a nuclear power plant, instead of burning something, just allows that uranium to split apart, and that releases the energy that heats the water, creates the steam, and then that steam is going up through a turbine. Those turbines spin to generate electricity, and the steam just leaves the top of the nuclear power plants. Some of the issues with nuclear power is not necessarily the actual energy generation, because that is pretty overall a very clean process when you compare that to the burning of coal or natural gas to make electricity. There are some issues, like number one, who wants this in their backyard because of accidents when the chain reaction has gotten out of control. If anyone has ever heard of Chernobyl, all right, Chernobyl is an example of a nuclear power plant that was running some tests and some diagnostics, and they weren't following the procedures correctly. They lost control of their nuclear reaction, and that's when it did explode. And now no one can live within, like a couple 100 miles of Chernobyl because it's so radioactive, because that stuff is going to take 10,000 or more years until the radiation drops low enough that people can actually live there. So these are obviously very, very diversive in terms of making people feel strongly one way or the other about nuclear energy. But it is pretty cheap, it is pretty clean compared to the other alternatives, so we may need to rely on nuclear power a little bit more in the future. Another issue with nuclear power is the leftover material. So eventually, once the uranium breaks down, we're left with radioactive waste, these chemicals that are not very good, and then the question is, what do you do with them? Because they're no longer going to go through fission, they're no longer going to generate enough electricity, or enough energy to generate electricity, and we're just left with them. So what are we doing with them? Well, currently we're trying to bury it, which is not necessarily the greatest idea, but in the United States, a lot of places out west, we just try and bury a bunch of this crap in the mountains and just hopefully forget about it. The issue there is that it's still giving off radiation. It's still causing the structures that we built to store them in to break down, because it even breaks down things like concrete after a while. So it's just very, very problematic with some of the waste that's left over. And then there's always that danger of an accident. But there could be accidents at in the other processes as well, right? Natural gas is extremely flammable, so that could obviously lead to some issues. And then coal mining is just an awful, dirty, dirty business for the people that are mining it and the environment itself. So nuclear power, while it has its issues, can be a very, very reliable source of energy in the future. All right, so that was fission. Fission was taking a really big atom that's unstable, giving it a little push, letting it break apart to release a huge amount of energy and smaller atoms. Fusion is another reaction that produces a huge amount of energy, but it goes about it in a very, very different way. Fusion reactions are already taking place on something very important to us. They occur inside the sun. The sun is powered by the process of fusion. In fusion, we're working the other way. Instead of starting big and going small, we're starting small and we're going big. So you take the nuclei of two very, very small atoms, okay? Our sun is taking hydrogen and hydrogen at this point, okay? Now they're called different things because they get adjusted. It's not quite hydrogen. It turns into something called deuterium and tritium. You don't need to understand that. Just understand these were once hydrogen atoms. So it takes two hydrogen atoms, crushes them together under immense heat and immense pressure, okay? And it produces helium, which is the next biggest element. So we're taking two very small ones, crushing those atoms together to produce helium, and then a huge amount of energy and some neutrons as well. Now, if you look, one key thing here is that we have a positive and a positive being crushed together. So that's why it takes extreme heat and extreme pressure, a whole bunch of energy and a whole bunch of force to actually crush these together to get them to stay together. That is the key. We can't do this to atoms. We can't overcome that repulsion force, because when you get those two nucleuses together, you're putting a very positive and a very positive core together. Those are going to want to push each other apart. They're not going to want to stay together. So fusion is incredibly hard to achieve. It currently requires huge heat and huge pressure. Now, there is a big race out there right now to try and figure out, is there a different way that we can get atoms to fuse together? Because it would still release a large amount of energy, and it would produce helium instead of radioactive waste. So there are reasons to want to figure out fusion and how that works. So we're kind of trying to race to try and figure out some of these problems for how we can get around that and use fusion to make electricity versus fission. So why can't we use fusion? Well, number one, it needs a huge amount of energy, more than it would actually, we could actually capture from that process. So currently we're operating at a negative budget. It would require more energy than we would be able to capture from it. Now, it'll produce more energy than we can capture. That's the key. If we could capture all of the energy, that would be different. But the key here is that it's not producing enough, or we can't capture enough energy from the end result, and therefore we can't sustain the process. We got to overcome those electrical forces. That's very hard. It's also very difficult to control and predict, okay? We've never produced fusion in a nuclear power plant. Nuclear power plants only use the fission process, breaking things apart. Now, this is going to change, okay? Like I said, there are scientists working on this. There's an idea out there called cold fusion, a way without immense heat and pressure to get those things to smash together and still produce the energy, but that's still in development. I guarantee the people who first discover a sustainable fusion generator will most likely win a Nobel Prize and become very famous, because it's really going to solve our energy needs overnight. Fusion, a small amount of fusion could power the entire planet many times over without any problems. So if we were able to extract all the energy that we can get out of a fusion reaction and produce fusion reactions on a regular and reliable basis, the energy needs would just kind of disappear of this world, not just the country, the world. So there's a big push to try and figure out fusion and if we can use it. So again, what are the benefits? It uses hydrogen. Hydrogen is the most abundant element in the entire universe. Everywhere we look, in every corner of the known universe, we see hydrogen. This goes back to the Big Bang, the idea that the Big Bang created two elements, hydrogen and helium. 75% of that is hydrogen, 25% of that was helium. So hydrogen is just everywhere. So we could have always, it's not like when we look for oil or natural gas, we can find hydrogen anywhere. Very, very important. And it could, like I said, meet the energy demands for millions of years. Like, we would just be set if we could do fusion. It would just kind of solve a lot of problems. Okay, let's skip over a bunch of very complicated stuff. All right, and we're going to get into Let me peek at the notes because this is the non-edited version. Good job. We pull up the non-edited version. All right, so you guys pick back up when we were just talking about. Oh, no, that's it. I lied. I just cut off the rest of it. Okay, so we can talk a little bit. We can use radioactivity as a tracer. Some elements break down naturally through radioactive decay, but they don't release a huge amount of energy, just release a little bit of energy. So we can use that if you've ever gotten like a bone scan or something like that. What they'll do is they'll inject into your bloodstream a radioactive isotope, something that's going to give off a little bit of energy. And then they use a very sensitive detector to see where the blood is going, because that stuff will be in the blood and the blood pools if you have like a broken bone. For example, when I was in college, I had 2 stress fractures in my ankle. The problem with the ankle is there's a whole bunch of bones really close together, so they really couldn't see where the break was using just a simple x-ray. So I actually had to have a bone scan. So they injected me with the isotope. I waited for a while, and they wait to see where the blood is pulling. You get a whole bunch of pings in the area where the blood is pulling. So that tracer, or that detector rather, senses all those things in the area where the break is, and then they can get a better idea of where the broken bone is. We can use it in agriculture to see where the water's going. We use it in medicine to locate tumors and stuff like that. In medical research, we can see where drugs are going. So I don't know how much you know about the body, but there's actually a barrier between the blood system and the brain, okay? It's called the blood-brain barrier. Some medications can pass that and in the brain, some stay in the body. So it's a good way to measure where things are going. In geology, we can use it to trace underground waters, where that's occurring and where it's flowing. This is very important because water is a very, very valuable resource. So we can use radioactive tracers in a whole bunch of different ways, but that's just a little extra information for yourself. All right, last but not least is all you have is the exit ticket. So go ahead and head over there. Just very simple questions, get that submitted. Like I said, tomorrow we will be reviewing for the final exam, which is all of the second half. Okay, so that's all of chemistry. So atoms, atomic structure, elements of the periodic table, Bohr and Lewis dot structures, ionic and covalent bonds, balancing chemical equations, and electricity and nuclear energy, fusion versus fission, which we just talked about. Okay, so the second 4 weeks. And like I said, we'll be reviewing that tomorrow, so tune in then, and I'll see you at that point in time. If you haven't made up any of your tests or stuff like that, please, 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 as soon as possible. This is the last week of the term. We are out of time. If it's really not done by Wednesday, it's going to be very hard for me to grade and get in the grade book so that you can get that passing overall grade. So make sure you get those done. If you have any issues or problems, reach out to me and let me know. Otherwise, have a great day.